one of the order of reaction is the zero order of reaction. Now, the rate law for zero order of reaction is given by this. That is the algebraic rate law. We have the rate of reaction being equal to K times concentration of the reactant raised to power 0. And of course, we know that a term raised to power 0 would give us what? 1. So the rate will now be K times 1. Now, what does that tell us here? You notice that the rate of reaction is equal to constant. So it means that for zero order rate of reaction, the rate of reaction is independent of concentration. Look at it. Okay? It is independent of concentration. Look at the graph plotted, the rate against concentration. You see that no matter the increase in concentration, the rate of reaction remains fixed at this point. So that tells us that for zero order rate of reaction, the rate does not depend on concentration. Alright, now we know generally that the differential rate law can be written in this form, generally, okay? Expressing the rate of reaction. So we can equate 1 and 2, since both of them are defining what? Rate of reaction. And if we equate it, the differential rate equation for zero order will be given by equation 3, where negative dCA over dt is equal to what? K. Is that okay? That's the rate of reaction is equal to K. It contains differential coefficient. That's why we refer to it as differential rate law for zero order. Take notes. Now, we can actually work on this differential rate law from equation 3 and obtain the integral rate equation for zero order rate of reaction. All we need to do is to separate the differential coefficient terms and then integrate from initial value to a final value. We have that actually on the board here. You can see if I cross multiply and then multiply through by negative, the negative goes here, then dt will multiply negative k. Now we shall integrate this from an initial value of the concentration of the reactant to a final value of concentration. Just think about someone that is trying to produce a soap. Okay, one of the process, the process of producing soap, saponification, we mix oil, right, fatty acid with a particular reagent. The reagent used in this case sodium hydroxide for the saponification process. So what happened? You notice that the concentration of the oil, maybe the producer would measure a certain quantity of the oil, then place the reaction system on fire, and then add up the sodium hydroxide. The reaction will begin. Over time, the quantity of oil that this producer used from beginning would reduce. You know that because once the soap starts forming, the oil concentration quantity will start decreasing. Is that okay? So the startup time, the concentration, we refer to it as CaO. That is initial concentration. That's what I'm using here. Alright, then Ca1 will now be the final concentration at a given time when the reaction has started. Does that make sense? Final concentration at any given time. Now, the initial point when the producer measured the oil before starting up the reaction, we refer to it as time 0, which is T0 here. T0, is that okay? Then at any given time, one can calculate the concentration. Maybe let's say, okay, after starting the reaction, what will be the concentration of the oil, of the sodium hydroxide left in 5 minutes? What will be the concentration in 10 minutes? What will be the concentration in 11 minutes? You know, things like that. We can actually determine it by integrating this equation. And doing that, look at the integral rate law now. You can see it, right? Given by equation 4. This is the integral rate law for zero order rate of reaction. If we have integral dCA, just like someone giving you integral dx, what will happen? It's going to welcome back the variable. So here, Ca will be welcomed back. Is that okay? So if integral dCA here will give us Ca, then it means that this term will give us Ca with the limit of integration from initial concentration CaO to final concentration at any given time Ca1. What do we do with limit of integration? We already have treated something like definite integral in your mathematics, okay? So we have to substitute upper limit minus lower limit, which of course would give us this. And that would be equal to negative k times t, following the same order. At the end of this is what we're going to get, moving the initial concentration because we know the value, which is what the producer, for example, of our soap example, is that okay, would have to measure before he starts or she starts the reaction. And so this CaO can be taken to the right hand side. It will be Ca1 equal to CaO minus Kt. So this equation 4 star is a very important equation for calculating the final concentration at any time for a given chemical reaction. Take note, for zero other. Now we can choose to plot a graph of concentration against time. If we plot the graph of concentration, we want to know how the concentration of the reactant changes with respect to time. We can actually get something like this. Alright, the graph would be something that goes inversely this way. It's a negative graph, just like you can see. It's a negative graph, okay? The slope of the graph will give us negative k, that is minus the rate constant, which means to get the rate constant k, it's going to be negative. The slope will obtain from here. And of course, the intercept will give us the initial concentration, CaO. In the next video, we're going to look at the half-life equation for this reaction. When the time gets to half, are you getting what would be the concentration at the half-life time? That's what we're going to look at in the next video. In this video, we now want to look at first order rate of reaction. Previously, we already treated zero order. Now, it's important to state here that first order rate of reaction, the analysis also goes in similar way as we already stated for zero order. The only thing is just for us to know the rate law equation, and then we will equate it to the rate law in terms of differential equation, then do the necessary integration that we are going to encounter. So on the board here, we have this, okay? For first order reaction, the algebraic rate law is given as this. So the rate of reaction of the reactant is equal to the rate constant times the concentration raised to power 1. Is that okay? Take note that this concentration is raised to power 1, and anything raised to power 1 will still give you that term. Is that okay? So just take note of that. Now, for zero order, the difference is that the power here is raised to power 0 because we are dealing with zero order there. So the concentration raised to power 0 gave us 1 times K, now left us with what? K. But in this case, we're going to have K times Ca because this concentration will survive since the power is what? 1. Now, we know that the rate of reaction in terms of differential equation is given as negative the Ca over the T. So this gives us room to equate 1 and 2 because both of them are defining the rates of reaction. So if we equate the two, we're going to have minus the Ca over the T equal to Kca, equation 3. Now let us look at this graph, please. Let us look at this graph. In the graph, we plotted the rate of reaction against what? Concentration. That's coming from equation 1 here. And you could see that this is a straight line equation with no intercept. It passed through 0 because there's no intercept here, you know, comparing with y equal to mx plus c. So this tells us that the rate of reaction is directly proportional to what? Concentration when you are dealing with first order rate of reaction. Remember, for zero order, it is a constant. It does not change even if the concentration changes, alright? But for first order, the rate of reaction changes with concentration and it is directly proportional. Now, equation 3 gives us the differential rate law for first order, and we can work on equation 3 to actually obtain the integral rate law. If we're working on that, all we need to do here is to separate our variables. Is that okay? Like in differential equation, ordinary differential equation, we're going to separate variables. This is the Ca, differential coefficient controlling concentration. So I'm going to move this concentration term Ca to this left-hand side. If it's coming here, it's coming as a divisor, that is denominator, so it's going to be 1 over Ca here. Is that okay? And then the T would go to the right-hand side of the equation. We refer to that as separation of what? Variables. If we do that, we'll get this. The negative sign also goes to the right-hand side by choice. So having done that, we can now integrate from the initial concentration to final concentration, and then from 0 time to final time, just like we explained for zero order rate of reaction. This equation 4 is our integral rate law. Take note. And if we integrate 1 over Ca, just like integrating 1 over x, you're going to get ln x. Is that it? So integral 1 over Ca will give us ln Ca. So we can now substitute upper and lower limit, CaO and then Ca1. The initial and final concentration, if you do that, we'll get this called negative Kt. So moving this lane CaO to the right hand side, we'll get equation 4A star, which is used to calculate the final concentration at any given time when dealing with what? First order rate of reaction. If we plot this lane of the concentration against time, look at it, you would get the slope to be negative of rate constant K, which means that K is equal to minus slope. Is that okay? And then the intercept will give us lane CaO. That is logarithm to base E of the initial concentration. The next video we shall look at the half-life equation for first order rate of reaction. In this video, we now take a look at second order rate of reaction. Now, when dealing with second order rate of reaction, we have the algebraic rate law given by equation 1 on the board. Okay, so what can you see there? It's giving us rate of reaction being equal to the rate constant times the concentration raised to the power what? 2, where the 2 is the order of the reaction. Then as usual, we can write the rate of reaction in terms of differential equation, which gives us equation 2. So if you look at this equation 2, it's a common thing in all the orders of reaction treated so far. Zero order, first order, and this time around, second order. So what do we do from here? We're going to equate this equation 1 and 2, and doing that we'll get equation 3. Remember, both of them are defining the rates of reaction. And so you can equate their right hand sides. So if we do that, we'll get equation 3, which actually defines the rates law in terms of differential what? Equation for second order rate of reaction. Now from this equation 3, we can now obtain the integral rate law by separating variables with respect to their differential coefficient. Of course, we have the dCA here. So if I take dt to this part, then our concentration should be controlled by what? The differential coefficient dCA. So I'm going to bring Ca squared to the left hand side of the equation, just like we did for first order rate of reaction. If I transfer that and then move negative sign to the right hand side, this is what I'm going to get. Take note that Ca squared is going to come to the left hand side as a divisor, hence a denominator. So we'll have it here. And we can integrate from the initial concentration to final concentration, and then from 0 time to what? Final time. Does that make sense? You can do well to remember our example of the producer of soap using oil and sodium hydroxide. Okay, now the oil is fatty acid, you know that. So if we actually substitute these terms into this integral rate law and doing our integration, this is 1 over Ca squared. How do you integrate it? You can think of maybe integrating something like 1 over x squared. If you're given this to integrate, you're going to change it to x raised to power minus 2, then you integrate. Is that not so? So how do you integrate this term? You know, this is like a power rule form. So you're going to add 1 to the power. If you add 1 to this power, you get x raised to power minus 1 if you add 1 to it. And then you divide by that new power minus 1, isn't it? So this term here, it's going to be something like minus x raised to power minus 1. Remember, you are dividing by minus 1. So that's division by minus 1 introduces the minus there. So if you integrate this term, what you're going to get will be minus Ca raised to power minus 1, which eventually will change to minus 1 over Ca if you take the reciprocal using indices law here. So that is actually what I got here, negative 1 over Ca. And then we can introduce our upper and lower limit. Now, keep this minus outside as it is. If you introduce upper limit, you have 1 over Ca1. Is that not so? Then minus 1 over Cao. I hope it makes sense, right? Then if you now open up the bracket with this negative sign, it will change the sign. Remember, you had 1 over Ca1 minus 1 over Cao. So it's going to change the sign to minus 1 over Ca1 plus 1 over Cao, which is still the same as 1 over Cao positive and then minus 1 over Ca1 negative. Everything equal to negative Kt. Are you following? So, looking at this, we are looking for the final concentration, so we can make this final concentration subject to the formula 1 over Ca1. To make this subject a formula, I can take 1 over CA1, negative of it, to the right hand side, it will change to positive. Then I will bring minus KT to the left hand side to come to this 1 over CAO. Of course, it's going to be plus once it crosses. So you see that all in all, making 1 over CA1 subject to the formula, it's going to be 1 over CAO plus KT. And this equation 4A star is the equation we use in calculating the final concentration for a second order rate of reaction. This one now bears reciprocals of the concentration terms, right? That is inverse, unlike the ones you've seen before. And then take note that between the initial concentration term and the KT term, you have addition for this second order. For first order and zero order, it was minus. I hope you take note of that, right? Okay, so please try to look at the forms in which the equations take. It's very important. If you graph 1 over the final concentration, that is 1 over concentration at any point in time. If you plot it against time, the graph you're going to get will be a straight line graph. And because this K is positive here, it's going to be a positive curve, like supply curve, right? The ones you saw for zero order and the second and the first order was a demand curve because the slope was negative. Here the slope is positive, so the graph is going to go this way. And as usual, if you take the slope will be equal to what? The rate constant. And then the intercept will be 1 over the initial concentration. It's now time in the next video we're going to look at the half-life for a second order rate of reaction.